Hi everybody, I hope you are all doing well and everything is okay on your side. In this chapter we are going to discuss DC circuits. First we will see the difference between AC circuits and DC circuits. Then I will talk about EMF and terminal voltage, power, series and parallel circuits. Then in the second part I'm going to discuss Kirchhoff's law, and in the last part you will see RC circuits where I'm going to discuss charging and discharging process. Now let's start with DC circuits. DC stands for direct current. Current goes in one direction, like this. Now if you consider a simple picture where we have battery and light bulb, so we have very simple circuit. All the electrons come out of the battery and flow around this circuit in one direction. So direction never changes. Batteries like these produce direct current. Let me give you an example. Now, let's say this is your laptop, and we have an outlet, 220 volts. When you plug it into the wall, actually you are plugging in its little power supply. It's your transformer that takes 220 volt alternating current and produces direct current. Let's say 10 volts. So all these little components inside your laptop use this direct current to run. Now if you plot voltage as a function of time, we have this constant voltage. So voltage is not changing as a function of time. Now for the AC circuits, so AC stands for alternating current. Current goes forward and backward. Actually, it's oscillating back and forth, like this. Let's consider the same outlet, 220 volt, and let's say we have a TV. When you plug your TV into the wall, electricity flows in one wire to the TV and then go back into the wall through the other wire. But they travel like that for a very short amount of time and for a very short distance. What I mean, if you have a 120 Hz TV, for example, and if you consider this little section of the wire, you could see electrons moving in one way, they stop, and then go back the other way, and then they stop again, change direction, and go back the other way again. So they are just switching direction all the time. So for this 120 Hz TV, for this small distance, they are switching direction 120 times per second. Now if you consider voltage as a function of time for alternating current, we don't see this constant voltage. Instead we have this oscillating voltage. The function is kind of sinusoidal function. I hope you understand the main concept of DC circuit and AC circuits. But we are not going to discuss AC circuits in this course, so we are going to mostly concentrate on DC circuits. So in DC circuits we have power supply and represented like this, and we have positive terminal and also negative terminal. So examples, batteries, cells, or generators. Now let's consider a simple battery. So inside the battery we have an internal resistance that we cannot get away from. So for this small internal resistance I'm going to use small r, and we have also voltage, epsilon. So again here small r is the internal resistance, leads to voltage drop. And this epsilon is EMF voltage or electromotive force. It's not different from the voltage you already know. So it's kind of a pumping mechanism, and it's pumping current into the system. So this is the textbook definition of EMF. So this is maximum potential delivered by a battery when no current flows through it. Now if you want to measure the potential difference of this battery, we do this. We put our voltmeter here. So this voltage here is called terminal voltage. So potential difference at the terminal of the circuit. This is the one we are measuring, and which can be defined as epsilon minus I times R. So here I is the current of the circuit. Now before going into detail, let's see what happens if we have more than one battery. Our first battery, second battery, and the third battery. Now this is the positive terminal, this is negative terminal, positive, negative, positive, negative, negative, positive. Now these two connect in the same direction, and this one is connected in opposite direction. These two are pumping current in this direction. This one is pumping current in opposite direction. So let's call the EMF voltage. The first one, epsilon 1, second one, epsilon 2, and the third one, epsilon 3. So the net EMF is epsilon 1 plus epsilon 2. They are in the same direction, and then we have minus epsilon 3. Okay. Now let's have more discussion. So I'm going to start with this simple circuit. We have our EMF and internal resistance. So this is our battery. Remember, this is our battery. And then we have also external resistor, capital R. Now the direction of current here is clockwise. The conventional current goes from positive terminal to negative terminal. Now let's call this point A and this point B. And this voltage here is called terminal voltage. So VAB is terminal voltage. So VAB is simply epsilon minus I times R, internal resistance. So I is simply epsilon over small r plus capital R. When you plug this equation in here, then you would get, so forget about AB, I'm just going to use V here, epsilon minus, so for I I'm going to use this equation, epsilon over capital R plus R times small r. If you take epsilon parenthesis, 1 minus R over capital R plus small r, and if you play it a little bit around, then we get this final equation, which is epsilon times capital R over R plus small r. Now let's see what happens when small r is much smaller than capital R, or we're going to see what happens when small r goes to 0 actually. So when you put 0 here, you see that terminal voltage is EMF. So when you remove internal resistance, so there's no difference between EMF and the terminal voltage. They'll be the same. But if capital R is much smaller than small r, or when capital R goes to 0, then terminal voltage goes to 0 too. So it's like we are sorting out the battery. Next, let's discuss power. Now again, I'm going to start with this simple circuit. So there's no internal resistance. We have our EMF, the same as voltage, because there is no internal resistance. And we have resistor R, and power can be defined, so this is direction of current, and the power can be defined as rate of change of energy, which can be described as rate of change of work. So we can write down work as Q times V, so which is dQV over dt. So since this one is constant, V is constant, so this equation can be written as dQ over dt times V. So here dQ over dt is current, so we can express power as I times V. Or we can re-express this equation as I times, from Ohm's law we can rewrite V as I times R. Now you see we get I squared times R. We have the same power with different equations. So we can use this or this equation or the second one. They're actually the same. Now if you consider this circuit, now we have internal resistance. So there's almost no difference between these two. So I'm just going to rewrite this equation with respect to this picture. So which is I squared times epsilon. So this coming from the first equation. Or if you want to express this in terms of I squared R, so I can just rewrite this equation as I squared capital R plus small r. Now the first part is the heat produced in the external resistor, so I squared R, and the second part, I squared small r, the heat produced inside the battery. Very simple definition and very simple equations. Now let's discuss series and parallel circuits. So you already know all these concepts in high school, but I just want to remind you all these simple equations. Now let's start with series circuits. So we have these three resistors connected in series. We have our power supply. We call these resistors as R1, R2, and R3. Now we produce current in this direction. Again, it's clockwise direction. So the current is the same for these three resistors. Now, but we're going to have different potential across each resistor. So let's call this potential difference V1, this one V2, and this one V3. Since I is constant and we want to calculate equivalent resistance, so we can express V as sum of these three potentials. So capital V, V1 plus V2 plus V3. Now in the big picture, V is from Ohm's law, of course, I times R equivalent. So V1 is I times R1, V2 is I times R2, and V3 is I times R3. So we have the same current, so they'll cancel out, and we are left with R equivalent equals R1 plus R2 plus R3. Well, if you have resistors in series, then the equivalent resistance is simply sum of all the resistors in your circuit. Now for the parallel circuit, let's draw this simple picture. Now we have R1, R2, and R3, and we have a potential power supply here. So since they are in parallel, the potential across each resistor will be the same. The potential across R1 will be V, and same for R2, and also same for R3. They're all V, but we are going to have different currents. The current will split in 3 branches. So I'm going to call this branch I1, this one I2, and this one I3. Now we have the same V, so there's no equation to start with V. So I'm going to start with I. So this total I is sum of I1 plus I2 plus I3. From Ohm's law, I can express total I as V over R equivalent. Now the same for I1, which is V over R1 plus V over R2 for I2, and finally V over R3 for I3. All the V's cancel out, and then we get 1 over R equivalent, 1 over R1 plus 1 over R2 plus 1 over R3. So if we have resistors in parallel, then we need to use this equation. Remember, for 2 resistors in parallel, we can find R equivalent as R1 times R2 divided by R1 plus R2. Now let's have a very simple example. We have this circuit. Now we have a battery with internal resistance. Now I'm going to have a bunch of questions for you. Find current passing through R1, and we're going to find current passing through R4, and the potential difference across R2 and R4, and we're going to find the power dissipated in R3, and also find terminal voltage of the battery. So to answer all these questions, first we have to decompose this circuit into a very simple circuit. So I'm going to work on the same circuit here. We're going to use R equivalent for parallel and series. So let's start with this. So R1 and R2 are in series. So I'm going to call this resistance as R12. Now we can reduce this circuit to this one. Now we have R12 here. Now let's first find R12. So they're in series. So R12 is R1 plus R2, which is 2 plus 4, and R12 is 6 ohm. Now let's consider these two. They're in parallel. Now we can reduce this circuit to this form. Now I'm going to call these R123. Now here we have R4, small r, and the battery. Now let's first find out R123. So which is, since we have only 2, so we can just use this simple multiplication and division. So we have R12 times R3 divided by R12 plus R3. So R12 is 6, R3 is 3. Now we have 6 times 3 divided by 6 plus 3, and we get 2 ohm. Now then we're going to consider these two. They're in series. So I don't want to include this R1 here, because this is the internal resistance of the battery. So R123 and R4 in series. Then we can reduce this circuit into this one, R1234, and the battery. Now let's first calculate R1234. So which is R123 plus R4, because they are in series, and we get 2 plus 5, which is 7 ohm. Now we can find equivalent resistance, sum of R1234 plus the internal resistance, 7 plus 1, and you get 8 ohm. So this is the equivalent resistance. Now if you have this, and if you have your voltage, then you can calculate your current. which is I times R equivalent. This is 16 volt. I times 8, and I is 2 ampere. Okay, now we have our current moving clockwise. Now let's put all these values: R12 6 ohm, R123 2 ohm, and R1234 7 ohm. Now if you know resistor and the current, then you can calculate voltage across the resistor. So I'm going to call this voltage V1234, which is I times R1234, and you get 14 volts. Now this is the simplest circuit we can get out of this complex circuit. Now we are going back. So I'm just going to take a look at this circuit. So you see R123 consists of R123 and R4, and they are in series. That means I have to get the current information from the previous one. So I'm just going to get this information. So that means the current of this circuit is 2 ampere 2. Again, if you know the current, then you can easily calculate the potential. So first I'm going to calculate this potential and call it V123, which is I times R123, and 4 volts, and V4 is I times R4, which is 10 volts. We can also calculate this potential across internal resistance, I times small r, 2 volts. Now we're going back. So R123 consists of R12 and R3, and they are in parallel, which means I have to get the voltage from the previous one, which means this voltage here, or V3, is 4 volt. Now I have the same voltage, V12, which is 4 volt too. Now you have the resistor and the voltage. Now you can calculate the current passing through each resistor. Now I'm going to start with this. I'm going to start with R3. So V3 is I3 times R3, which is I3 times 3, and I can get I3 as 4 over 3 ampere. The same way, V12 is I12 times R12, which is I12 times 6, and now I can get I12 as 2 over 3 ampere. Again, we're going back, so we get all the information for R3, R4, and small r, and but we need to find the information for R1 and R2. We're just going to concentrate on this. So R12 consists of R1 and R2. They are in series. That means I have to get the current information from the previous circuit. So let's do that. Now the current for these two is 2 over 3 ampere. Then I can calculate voltage drop for each resistor. So V1 is I times R1, which is 1 over 3 volts, and V2 is I times R2, and 4 over 3 volts. Now we have all the information. So we can get all these answers very easily for the first part. So current passing through R1 is right here, which is 2 over 3 ampere. And current passing through R4, let's find out. So which is 2 ampere here. And the potential difference across R2 is right here, 4 over 3 volts. And the potential difference across R4 is 10 volts. And the power dissipated in R3, so this is this current, which is I3 squared times R3, then 4 over 3 squared times 3, and we get 16 over 3 watt. And finally, the terminal voltage of the battery, so epsilon minus IR, and epsilon is 16 volt, minus 2 times 1. The current is 2 ampere right here. It's passing through R, small r, and the final result is 14 volts. You see, if you decompose this circuit into a very simple circuit, from there, if you go back using parallel and series information, then you can get all the answers very easily. When you go back, you have to check whether they're in parallel or series. When they are in series, you have to get the current from the previous one. If they're in parallel, you have to get the potential from the previous one. That's all you need to do. There's one more example that you can easily get. So I'm not gonna give you the detailed solutions. You can easily get all these answers. You already have the decomposed version of this complex circuit and try to get all these answers.